Hello. In this video, we begin to deal with what I think are some of the most difficult aspects of probability theory. In particular, we are now going to explain how probabilistic models should be interpreted. Central to this is a theorem called the law of large numbers, and thus by the end of this video, you should be able to state this theorem and explain why it is useful in the context of interpreting probabilistic data. There are a number of reasons why I think this material on the law of large numbers and the interpretation of probability is so difficult. First of all, there is still active debate in the statistics literature concerning how probabilistic information should be interpreted. In particular, there is much discussion between the frequentist and Bayesian perspectives. I think what is more pertinent to this case, however, is the fact that we are taught the classical interpretation of probability pretty early on in our mathematical educations. This explanation of the meaning of probability is simple, straightforward, and compelling, and we thus wonder at why these more elaborate and confusing Bayesian and frequentist pictures are necessary. We must remember, however, that the classical interpretation of probability is incomplete. When we introduce experiments such as shooting an arrow at a target and looking at the chance of hitting the bullseye, we quickly end up having to calculate infinity over infinity, which, as we have seen in previous videos, is not possible using our conventional rules of number. This realization led us to introduce a new definition of probability based on the existence of a cumulative probability distribution function. This function was defined by stating that if each event S in the sample space omega has a value x of S taken from the set of real numbers, script R, then there exists a cumulative probability distribution function that maps each subset of omega that can be formed using this piece of set builder notation to a number from the set of real numbers between 0 and 1. This function has the following three properties. Its limit as you go to minus infinity is 0, its limit as you go to plus infinity is 1, and it is right continuous. This is all extremely abstract, however, and there is now no simple connection between the cumulative probability distribution and the experiment that gives us the random variable capital X as its outcome. If you think about it though, even when we use our classical interpretation of probability, there is no predictive value in the insight we obtain from this alone. For example, suppose a psychopath tells you that he/she will decide to kill you based on the toss of a fair coin. You know that the coin will come up either heads or tails, and you know that these two outcomes are equally likely. This tells you nothing about how to ensure you survive this rather terrifying encounter, however. What purpose then does probability serve? Well, we can begin to see the purpose by considering this tossing of a coin a bit further. If we only toss the coin once, then the probabilities, the fact that the coin is fair, has zero predictive value. If we toss the coin more than once, however, and if the outcomes we get for the various tosses are independent, this probability is considerably more useful. As the coin is fair, we know that there are four equally likely outcomes: heads, 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 tails, tails, heads, and tails, tails. In two of these, you get only one head and one tail, and thus we can say that it is slightly more likely that you will get one tail rather than two. Taking this sort of thinking to its extreme, we arrive at a result known as the law of large numbers. This theorem tells us that if we generate an infinite number of random variables from the same underlying probability distribution, and if each of these random variables is independent of each other, then, once we add together all these random variables and divide by the number of experiments performed, we get the expectation. In other words, if we add together an extremely large number of random variables, which all have the same underlying cumulative probability distribution function, the result we obtain is not random. It is instead equal to the expectation of the random variable. This result, the law of large numbers, is written as shown here. We have the limit as n, the number of random variables we have generating, tends to infinity of a probability. The probability in question is the probability that the modulus of the difference between the expectation and the sum of all the random variables we generate, Sn, divided by n, the number of experiments, is greater than or This is the probability that this modulus of this difference is greater than a very small number known as epsilon. In the limit as n tends to infinity, this probability is equal to 0, and it is thus impossible for Sn over n to be equal to anything other than the expectation. This is a profound result. It is essentially saying that despite the fact that all the individual experiments give random results, the final compound result from all the experiments is predictable and can be obtained by taking the expectation. Now remember that the expectation is a summation if the random variable is discrete and an integral if the random variable is continuous. These quantities may well be infinite. The whole business of probability is not so useful in these cases. In many cases, however, the sum integral, the expectation, takes on a finite value. In these cases, the result from a very large number of repeated experiments, random variable generations, is thus completely predictable as a consequence of the law of large numbers. As we will see, this realization that we can predict the outcome of a large number of experiments by calculating the expectation of a random variable is useful even when it comes to understanding historical information. To see why, consider the following statement. Tomorrow there is a 50% chance of rain. Pause the video for a moment and take a moment to think about what this statement means. Does it mean that I should take an umbrella with me? If so, what is a low enough value of the probability of rain for me not to take an umbrella? I don't know what you came up with as your definition, but I would say that this statement means something like this. In the past, on days where the weather conditions have been similar to those that we are experiencing at the moment, it has rained half the time on the following day. In other words, weathermen have essentially collected data on rainfall patterns and the prevailing atmospheric conditions, and noticed that half the time, when the atmospheric conditions are as they are today, it rains on the following day. This is a rather complicated statement, but is one that we deal with every day when we watch the weather forecast. In making it, we make all sorts of assumptions about the universe, the biggest one of which is that we can use historical information to make predictions about the future. When we decide on whether or not to take an umbrella, we make even more assumptions. In fact, when I think of the weather forecast in this probabilistic way, I have no idea whether a 50% chance of rain means I should take an umbrella. I certainly have no clue as to where I should put my threshold on the probability at which I do not need an umbrella. My sentiments on the umbrella may seem odd, but I would argue that many of my fellow humans agree with me, but perhaps do not understand that they are doing so. Many weather websites that run for profit realize that people do not fully understand what a 50% chance of rain means. These companies have discovered that if they say that there is a 10% chance of rain, their customers assume that this means that it will not rain, when it means no such thing. They thus feel rather aggrieved if they go out on a day where the chance of rain is predicted to be low and it then rains. In fact, they may well, as a result of such an experience, stop using the service that gave them, in this mind, a poor prediction of the weather. This is a disaster for the weather website, as they make money by maximizing the traffic through their website and ensuring that as many people as possible see the advertisements presented therein. For this reason, a number of websites has deliberately chosen to overinflate their predictions of the probability of rain in order to keep their customers. The probabilities of rain on some websites thus do not even reflect what has been found from past atmospheric behavior. I mention this because it is important to realize that whenever we make predictions based on data from historical experiments, we can only understand the data from these experiments by introducing a random variable. I represent this using this diagram. When we take our experimental data, we make assumptions and insert this into a probability model. It is only when we have these two things together that we are able to make any predictions about the future. At the heart of all this fitting of models lies, once again, the law of large numbers, and the fact that if you do a large number of experiments, The outcome of all those experiments when taken together is completely predictable. This is why the law of large numbers is so important, and why it is so important that you must be able to explain why the expectation of a random variables are useful by making reference to the law of large numbers, which is as follows. I hope you've been able to understand this from this video. If not, try watching it again and see if you understand better on the second time through. Thank you.